Hello, and welcome to the Minute Physics tutorial on basic rocket science. Before we get started, I'd like to quickly announce that I'm now making these videos at the Perimeter Institute for Theoretical Physics, so keep your eyes out for plenty of upcoming videos about string theory, black holes, the Higgs boson, and so on. Now, back to rocket science. Okay, this is going to be a super simplified version of the basic dynamics of a rocket. We're going to start with a rocket, and the rocket we're going to assume has some fuel in it, and the whole rocket together with the fuel is going to have mass m. At some point, the rocket's going to ignite its engine, start ejecting fuel, and hopefully it will take off. And it will have a velocity, v, in the upward direction, and the exhaust will have a velocity, called the velocity of the exhaust, going down. Now, on top of that, because we're on Earth and not in the middle of outer space, the whole rocket and fuel system, everything together, is going to be affected by the force of gravity. So how do the dynamics of this system work? Well, you've probably all heard of F equals ma. Force is equal to mass times acceleration. Now in this case, what it means is that the force acting on a system causes an acceleration or a change of velocity of the system. And you need a bigger force to move a bigger mass. And that's why the m is in there. So we're going to start off by looking at the case before any of the fuel starts ejecting. It'll just be the rocket with mass m. So the total force is the force of gravity, and the force of gravity is equal to the mass of the object times the gravitational acceleration. And that's equal to, of course, ma, which is just the big M again, times the acceleration. And it's negative because the force of gravity is in the downward direction. Now, in this case, the acceleration is negative the acceleration from gravity. Basically, if the rocket's in midair and it's not firing, it's going to start falling down at a rate of 9.8 meters per second squared. So after the rocket ignites, not all of the mass will be in the rocket anymore, because some of it will be out here in the exhaust that's been shot out. In this case, the total force stays the same because it's still minus the total mass times gravity. But instead of just writing ma on the right side again, we now have two separate masses, the rocket and the exhaust. So we have to add together the mass times acceleration of each. Now the mass of the rocket is m minus some rate of fuel loss, which we'll call r, times the amount of time which has passed. Basically, r times t will tell you how many kilograms of fuel have shot out of the rocket as exhaust by time t, and the whole mass, m minus rt, is multiplied by the acceleration of the rocket. We also have to take into account the mass from the exhaust that came out. And we just said that the exhaust comes out at a rate r kilograms per second, so its mass is just r times t. So now what's the acceleration of the exhaust? Well, the definition of acceleration is the change of velocity in a given time, and the exhaust goes from moving with the rocket at velocity v before it's expelled to moving with the velocity of the exhaust after it's expelled. The change, or difference between those, is negative ve. It's negative because the exhaust is moving down. Minus v divided by the amount of time that's passed. So the t's cancel, and this equation tells us how the whole rocket plus exhaust system moves, where this part is the mass times acceleration of the rocket itself, and this part is the mass times acceleration of the exhaust. Now suppose you're launching a water bottle rocket, or trying to levitate by vomiting. How much fuel, which in this case is just water or milk, do you have to expel to take off? That is, to just barely beat gravity and begin to hover. Well, if you're just hovering, that means your velocity is 0, and your acceleration is 0 too. So all the parts of this complicated equation having to do with the rocket go away, and we're left with a much simpler equation describing just the exhaust. m times g equals r times ve. Remember, we're trying to determine how much water needs to be expelled in order for the rocket to hover. But now we have two variables which are trying to tell us that. R is the rate at which the exhaust water leaves the rocket, and VE is the speed it has after leaving. Those sound pretty similar. Let's see if we can figure out a way to relate them to each other. On the bottom of the rocket, there's probably a circular opening with area A, where the exhaust comes out. And since liquids like milk and water are incompressible, they'll take up the same volume when they come out as when they were inside the rocket. So there'll be a stream of water exhaust shooting out of the rocket, and in 1 second it'll go a distance VE. That's the velocity of the exhaust. This stream is roughly a cylinder, with the volume A times VE, measured in cubic meters. How do we relate this volume to the rate R of exhaust leaving the rocket? Well, R tells us the number of kilograms of water, and a kilogram of water takes up a liter of space, and there are 1,000 liters in a cubic meter, so R is just 1,000 times the volume. Now that we can relate both R and the velocity of the exhaust to the volume of the exhaust, it's just simple algebra to plug this into the equation describing the exhaust. Do a little multiplying, dividing, square rooting, and we've solved for the volume. All that remains is to plug in numbers for m, the total mass of rocket plus fuel, in kilograms, and a, the area of the opening at the bottom of the rocket. Hint, it's probably a circle. So what are you waiting for? Go weigh yourself, measure your throat, and find out how much milk you'd have to vomit in order to levitate. And if you want, you can share your personalized levitation-inducing milk vomiting rate in the comments below. Thanks for watching.